Okay, good morning. We'll just jump right into it, unless there's any questions before we get started. Okay, if not, sorry about that. I turned off my audio instead of my video. So what I was saying was we're going to keep talking about derivatives today. And so as I said last time, sometimes there's a few things we're going to recall from the theory of locally convex spaces, and I'll try to remember to collect those at the beginning of the lecture. So here's one that we're going to use today, maybe, depending on how far we get. And if not, we'll use it next time. And the fact is this. So I have a locally convex space, of course. And I'm going to say that a set B is what I'm going to call weakly bounded if when I take any element of the topological dual and I restrict it to be that's bounded as a function. So that's what weakly bounded means. So you remember that bounded means there's two nice characterizations of bounded. One is that a set is bounded when it can be absorbed by any zero neighborhood. Okay, so if you take a zero neighborhood and you expand it by a scalar multiple of sufficiently large magnitude, then it will B will be contained in that um, expanded zero neighborhood. All right, so that's one definition of bounded. The other definition of bounded is that if you take any continuous semi-norm and you restrict it to B, then as a function, that's bounded. All right, so that second definition looks quite similar to this, but here we're taking elements of the topological dual and we're restricting them to the set, and that's bounded. So in other words, what this is saying is that the property of restricting either elements of the topological dual or continuous semi-norms, that those functions are bounded is equivalent, actually. It's not entirely obvious. And this fact follows, so if you have a sort of introductory but not too introductory course in functional analysis, you'll know about the Banach-Steinhaus theorem, which is also sometimes called the uniform boundedness principle. And this can be proved for the using the Banach-Steinhaus theorem. And so there's a proof of this in the course text if you want to take a look at that. Okay. All right, so on with derivatives. So we've talked last time about curves, and we spent some time talking about the weak integral, and with the weak integral we were able to prove some basic and very useful facts using the weak integral. So for example, we proved the continuity of the weak integral on parameters of the integrand. And we proved the fundamental theorem of calculus using properties of the weak integral. Okay, so the weak integral is a very convenient tool for talking about analysis in locally convex spaces, and we're going to see that theme continuing today. So if you're looking through the course text, you'll see that there's a section there that you'll see that there's a section there that I'm not covering, and that section is about curves and boundedness. So if you want to see something less trivial than the things we talked about last time, take a look there. Okay. All right, so today we're actually going to talk about derivatives, not of curves, but of mappings. Between locally convex spaces. All right, so I'm gonna, if I don't tell you anything, then U and V are both locally convex spaces. And we're gonna take an open subset O Okay, so that's the notation that'll prevail in the lecture today, unless I indicate that those symbols mean something else. Okay. Right, so as I indicated during the motivation last time, the way we're going to define differentiation of a mapping between O and V is we're going to use directional derivative. Okay, so let me just give the definition and we'll talk about it. We'll talk about it a lot. Okay, so a mapping. So let me maybe mapping V from O into V is differentiable at x naught in O in the direction U, little u in big U, okay, if, okay, this limit exists. So limit as t goes to 0, phi of x naught plus tu minus phi of x naught over t. Okay. So notice that as long as t is small enough, then x naught plus tu is in O, sorry, so because O is open. Okay, so this the numerator makes sense. And notice here that t, so last time we talked about curves, and using the symbol t kind of suggests maybe we're talking about t as being real, but I'm actually going to allow t to be here. Okay, so these are right. So the locally convex spaces are vector spaces over F, where F is either R or C, and so we're going to be talking about so differentiable at O in the direction U. Okay, so we're going to be talking about not just real differentiability, but also complex differentiability, because turns out it's really no harder. Okay. Okay, so that's differentiability at a point in a direction. Okay, and we're going to denote this limit if it exists. So denote the limit when it exists by little d phi of x u. Okay. All right. So there's lots of different notation that
it's
yeah, please.
differentiable at x0 if this limit exists in the F.
I'm sorry, say that again.
I was just wondering, we said this is differentiable. The mapping is differentiable if this limit exists, or
Oh, well, sorry, I just forgot the word. Yeah, sorry, thanks. Yeah, yeah. Yeah, thank you.
in the
So the limit is in V, right?
okay.
Yeah. Yeah. So this is just, a normal limit of a thing in a locally convex space. Okay. Is that everyone okay with that?
Yes, thank you.
Okay, good. Thanks. Okay, so we're going to denote the limit by this notation. Okay, and we'll talk about this notation because last time I talked about the Jacobian d phi of x, and we're going to talk about the relationship between big D and little d. But this is the notation we're going to use now. And so the notation you'll notice includes the point, and I should say that's at x naught. Okay. So the notation includes the point at which I'm differentiating and the direction in which I'm differentiating, okay? The normal directional derivative. So now you will know again, from your elementary calculus course, and I'll give you a chance to remember your elementary calculus course in the homework, that this is a very weak notion of differentiability. And so you can have situations where the derivative exists at a point in every direction, and the function is not even continuous. Okay, so this notion, just derivative at a point in a direction, this is a very weak notion, and in fact, for the purposes for our purposes here, it's too weak. All right, so what I'm going to do, we're mainly going to be interested in things which I'm going to call continuously differentiable. So let me say what that means. Okay, so phi from O to V is continuously differentiable if d v x u exists for every x u in O cross u. Okay, so when I say d phi of xu exists, of course I mean that the limit in the previous part of the definition exists. Okay, and the mapping d phi from O cross u into V is continuous. Okay, so we'll also say the phi is of class C1. Okay. Right. And so this is a little bit different already than what we talked about last time. So last time we again talked about the Jacobian, capital D phi, and we said that continuous differentiability meant that the Jacobian was a continuous function of x. So this is different, and we'll talk about the ways in which it's different. Okay. All right. So let's establish a few basic properties. Oh, and so there's notation here that I use, and I've already not been consistent with it here. So it's useful sometimes, and I'm going to keep track of this because I want to really keep track of the fact that we're doing calculus here over both R and C. Okay, real and complex. And so I will try to remember to put the subscript F there, right? And on a few occasions, we're going to distinguish between R and C and see some relationships between those. And so I want to include that there. Okay. And the notation C1F. Okay, but I'll warn you because I don't often do this. I'm mostly in my life I deal with real things, and so I will normally just write C1. And so I may do that when I write things down. I've tried to be careful in the course notes, but during the lectures I may forget that. So be ready for that. And the notation we're going to use, of course, is C1 of O semicolon V. Like that. Okay. All right. So let's prove some stuff. Okay, so a basic fact, which gets used to do a lot of things, and it really illustrates the value of the business with the curves that we talked about last time, is the mean value theorem. And so in any sort of rigorous treatment of multivariable calculus, the mean value theorem is always important. Okay. All right, so with my abiding notation there. Okay. Um, let's let x1, x2 be in O. Okay. Such that the line, okay, between x1 and x2. So this is 1 minus t x1 plus t x2. Okay, so that's the line that connects x1 to x2 so this is a real line now. Okay. Okay, keeping in mind, complex vector spaces are real, so this makes sense for um, real or complex vector spaces. Okay. Such that I should say this thing is in O for every t between 0 and 1. Okay, so I have my open set O, and I'm considering 2 points where the line between them stays inside O. And so, for example, that couldn't be these points. And so, for example, if O was convex, then this is automatically true. Okay. All right. Okay, so now so what's the statement? So the statement is this. Okay, phi of x2 minus phi of x1 equals interval from 0 to 1 d phi of x1 plus t x2 minus x1. Okay, so x1 plus t x2 minus x1 is just a rewriting of that. Okay. All right, so d phi, and so this is my first argument of d phi, and d phi wants 2 arguments, and the other bit is x2 minus x1 dt. dt. Okay, so that's the mean value theorem. Okay. All right, so let's prove it. And so you won't be surprised to learn, I hope, that this is just falls almost immediately from the fundamental theorem of calculus that we talked about last time. Okay, so we're going to take the curve gamma. Okay. So since phi is of class C1F, okay, this limit, and now the t here is real in this case because gamma is a real curve. This limit exists. Okay, because that, after all, is really just a rewriting of that. Okay. Okay, and moreover, okay, so let's okay, and so this limit exists, and this limit exists for at every t. Okay, so we're gonna this limit exists for every t. So sorry. Okay. And so what I'm going to do is I'm going to write the derivative of gamma at a particular point, T naught. So
Sorry, I had a question.
yeah, sorry.
Did you mean to say that it exists for every A?
For
Because
every,
because T is moving in this instance.
you mean,
I think the limit of
no,
h goes to
I think
0.
I mean T here.
But in the limit, T is moving, right? T is the thing
Yeah,
which
so
is
I'm just
changing.
saying fix a T, then that limit exists for that T.
Okay.
Okay? And that's just, again, that's just uh, um, uh, because of the definition of gamma. Okay, and so maybe let me. I think I see what your point of confusion is. So let me say that a little bit differently. Okay, so and this is kind of where I was going anyway. Okay, we're going to take gamma of um, of okay. Okay, so sorry, I have to get my arguments right here. Okay, so I'm going to take the curve. So I'm going to go, let me write it down and then I'm going to do this. Right, so I'm going to fix a T naught, okay, and then vary T. And I think this kind of answers your question. Okay. Okay, so and so this is gamma now. So when I take the limit as in this equation as t goes to 0, what I'm going to get is I'm going to get gamma prime at t naught. Does that make sense?
Yeah, like written out like this, I mean, the idea is very clear, right? It's just
Yeah. So,
it's
but so that's so that when I when I say that this limit exists, I'm really using it in this form.
yeah, it's just that when you say that that limit exists, like what's the letter in the denominator?
That's an H.
H. So H is the thing that's moving in that limit.
I'm very sorry. No, you're that's just a typo. I'm very
Yeah,
sorry. Of course I mean H here.
yeah. Okay.
Yeah, I'm very sorry about that. Yeah.
Yeah.
I didn't notice that.
So should the
Okay.
denominator be also h?
Of course I would do that. Yeah. H. Good. Thank you.
Thank
All
you.
right. Is that okay now?
Yep.
Yeah, sorry. I missed the fact that I'd written it to
Yeah,
you.
so no, I was trying that's why I was confused like initially.
Yeah. No, that's my fault. I'm sorry. Okay. Um okay, and so so when I take this limit, what do I get? So the limit now I'm taking, and this is why I was getting myself confused, is now I'm taking the limit as t goes to 0. Okay, and so t here is playing the role. A little t in this equation is playing the role of h in that equation. Okay, so this is d phi of x1 plus t naught x2 minus x1, okay, and then x2 minus x1, okay, right? And so therefore this shows that gamma prime of t naught is d phi of x1 plus t naught x2 minus x1, x2 minus x1. Okay. All right. So now use the fundamental theorem of calculus that we proved last time. Okay, and so the fundamental theorem of calculus says that gamma of 1 minus, and so I'm going to have to, let me just, yeah, let me just make sure I have that right. Gamma of 1, yeah, okay, sorry, that's good. So gamma of 0 is integral from 0 to 1. Gamma prime of t dt. Okay, so plug this into there. Okay, and then notice that gamma prime of 0 is phi at x2. Sorry, gamma of 1 is phi of x2, and gamma of 0 is phi at x1, and that gives the result. Okay, so sorry, I kind of made more work of that than I needed to. Okay, does that make sense though? Did I? Okay.
Yep.
Okay, good, thank you. Okay, so that's the mean value theorem, which is really just the fundamental theorem of calculus. Okay, good. So the mean value theorem has one nice immediate consequence. Okay, and that is that mappings that are continuously differentiable are continuous. Okay. All right. So if phi is C1 mapping from O into V, then phi is continuous. Okay, so that's relatively easy to prove in normal calculus from the normal definition of the derivative. But things are a little bit different here because our definition of the derivative is a little bit different, and so we use a different proof than normal. And what we're going to use is we're going to use the continuous dependence of weak integral on parameters. Okay, so we're going to combine the mean value theorem with the continuous dependence of the weak integral on parameters. Okay, so here's how you do it. So let x naught be in O, okay, and let n be a convex neighborhood of x naught. Okay, so I know in a locally convex space, every point has a convex neighborhood, okay, and O is open, so that neighborhood can be chosen to be in O. Okay, so by mean value theorem, we have, so let me, sorry, phi of x minus phi of x naught. Okay, so I'm literally just transcribing the mean value theorem. And so I tried to be consistent with doing this, but again, it's one of those things that I'm apt to forget to put the W in front of the integral sign because that's the weak integral. I do that again in other parts of my life. I use other integrals besides the weak integral. So so it's x naught plus t, x minus x naught, x minus naught, dt. Okay, so that's just a transcription of the mean value theorem. Okay, and I'm going to ask that this holds for x in n. Okay, so now I'm using convexity of the neighborhood n. All right, because I need for this line here to remain inside n. All right, now. Okay, so note that this mapping um, and I really need okay, and so this is t is between 0 and 1 cross n. Okay. Okay, so this mapping, depending on two variables, t and x, okay, so I'm regarding x naught here as being fixed. So as a function of t and x, this expression is continuous, okay, and it's continuous. All right, so this is easy. Why is it continuous? And of course, I don't mean phi here, and neither I mean d phi. Apologies, d phi. Okay, so but still, why is it continuous?
It's a composition. You can write it as a composition of continuous maps.
Yeah, so there's a bunch of compositions here, right?
Yeah.
So d phi is
Yeah.
certainly continuous. And this argument is continuous in x because of continuity of addition, right? And similarly, this is continuous in x because of continuity of addition. And similarly, it's continuous in x and t because of continuity of addition and scalar multiplication. So, you know, it's continuous. You have to be sometimes a little careful with working with locally convex spaces to make sure that all these things that you take for granted are still true. So you would look at an expression like this and you wouldn't even bat an eye that this is continuous, but you should think about it for a second.
I think it's incredible that already that you have to prove that a continuously differentiable map is continuous.
Yeah. So that's that's
That's
right.
already like messed up.
So there's as we'll see when we look at an example, there's kind of a reason why you want to do that.
Right.
Yeah. But yeah, I'm getting a little ahead of myself. Okay. And so, therefore, so by continuity of weak integral on parameters, okay, because x here is like a parameter with respect to the weak integral. Okay, phi is continuous. Okay, right. So I just use this expression here. This certainly that's constant, and so when I and then this thing is continuously depending on x. Okay. All right, good. So I want to point out one thing here, which is different from, again, multivariable calculus that you're familiar with. So what do you do in multivariable calculus? There's actually the statement that you make there is much stronger. The statement that you make there is that if a function is differentiable at x, okay, then it's continuous at x. Right? So we're making a stronger a statement with stronger hypotheses, so therefore a weaker statement than that. We're saying that if phi is C1, okay, so we're assuming continuous differentiability on the whole domain in order to get continuity at a point, okay, and you know once it's continuous at a point, then it's continuous everywhere. So this is not exactly the statement that you learned in multivariable calculus. It's different, okay. And that's why there's many reasons why we're only going to talk about mappings that are C1, okay, not just differentiable, okay. So, you know, another reason is that you know we're mainly interested in geometry, and in geometry you're interested, you know, you're not so much interested in things that are, you know, continuous but not differentiable, and things like that. So C1 is, and in fact, very often in geometry, you work with things that are infinitely differentiable, but we haven't said what that means yet. Okay.
Is there a counterexample for the situation where phi is differentiable at a point but not
Yeah, I
continuous?
mean, I mean, even see, this is see that and there's two parts of what you're saying. Because we haven't defined what it means to be differentiable at a point, right? We've only defined what it means to be differentiable in a direction at a point,
Aha,
right? And
right.
so then your question is, if it's differentiable at a point in every direction, is it continuous? Then you know the answers to that is false, even
False, yeah.
in normal vector calculus.
Mhm.
Yeah, so yeah, so I mean, there's little subtleties in this theory of differentiability here that you can walk over them without noticing them if you don't think about it. So questions like that one are interesting to reflect on.
Okay.
Yeah. Okay. But if you just talk about things that are C1, life is good, or relatively. Okay, good. So that's one property of C1 functions. Um, um, okay, so what are some other properties of C1 functions? So let's maybe do this logically, which I don't always do, and prove. So one of the things that you would like is for the derivative to be, so where's my, okay, so it's a function of these two arguments, x and u, in O cross u, okay? And from normal calculus, it is the derivative is a continuous function, sorry, a linear function of the vector variable. Okay, and in fact, the normal way you build this is it's automatically a linear function because you take the Jacobian, big D, and you multiply it by the vector. Okay, but in here we're just working with this as a function of x and u, and so you have to prove linearity in u. Okay, so let's prove one part of that. Let's prove linear with respect to scalar multiplication. Okay, so d phi is homogeneous in the second argument. Okay, so what I'm proving here is this. So d phi, so I should say clearly here. So if phi is C1, then d phi of x a u is a d phi of x u. Okay, so that's what I mean by homogeneous. So this is relatively easy. Okay, so d phi of x a u by definition is limit as t goes to 0. And here, so in the previous situations with the continuity result and with the mean value theorem, t was real because I was working with curves. Now I'm back to the normal situation, so t is not necessarily real. Okay. So we're going to look at this. Okay. So this is oh
I guess
gosh.
you want T
Yeah,
in
yeah,
the
yeah.
denominator.
Thank you. Yeah. T. Yeah, I was anticipating the next step because what I'm going to do. So I should be, a little pedantic here, and let me assume that a is not 0. Certainly when a is equal to 0, this is obviously true. Okay, so let's assume that a is not 0. Okay, so when a is equal to 0, just to clarify, both sides of this expression are trivially 0. Okay. So what I'm going to do is I'm going to multiply by a and divide by a. Ah, okay. So again, a comes out of the limit because I can because of continuity of scalar multiplication. All right. So there's a little step there. All right. And so the point is now that t goes to 0 if and only if. So a here is fixed, right? So it's a fixed constant, non-zero. And so t goes to 0 if and only if at goes to 0. Okay, so this is the same thing as a limit, and let me rewrite the variable as s just to make it clear that I've done something. Okay, and this is the result. Right. So that's one part of linearity. We'll prove the other part as well. And to prove the other part, we're going to prove a little trick first. And this little trick is, it's a handy little trick. And we're going to use the trick in to do two things in a slick way. You can do the two things in a less slick way. That's sort of more direct and maybe more familiar. But it's interesting to do them slickly, because the slick trick is actually useful in some other areas that we may not actually get to in the course, but are interesting anyway. So it's good to sort of see this little slick trick. Okay. All right. So the slick trick I'll call characterization. And so, for example, this trick in that section I referred to about curves at the end of the subsection at the end of the section on curves that I referenced about some more complicated and deeper facts about curves. This notation shows up there and is very useful. But we're going to just do elementary things with it. Okay. Okay, so define. All right, so what do I have? I have the usual thing. I have phi is in C1F O V. Okay, define O, sort of weird notation here. So these are brackets that are pointing in the opposite direction from what you'd like them to point in. Okay, and so this is going to be the T's, the X's, and the U's in F cross O cross U, such that X plus TU is in O. Okay, and so when you calculate the derivative, you write down, or the limits that you calculate with the derivative, you have the thing X plus TU. So I'm just making sure that the things I'm about to write down make sense. Okay, and I'm also going to define phi 1. Oh, I apologize. In this one, X is T, sorry, is non-zero. Okay, and that's, the backward parentheses here are supposed to, sort of, this is like a thing that's closed, and so this is a thing that's open, and you'll see why. And so I'm going to include 0 in this one, but 0 is not included in this one. So if you want to try to give a rational explanation for this notation, that's what it is. Right? So this one is the same thing, except 0 is included. Okay. And so, and the reason that you exclude 0 here, of course, is when you talk about the difference quotient, you have that, the t is going to appear in the denominator, so you want to exclude it. Okay, now, okay, so these are now sets, okay? Sets of, parameters t, parameterizing, sort of curves, x's and v's, so points and directions. Okay, and then I'm going to define phi 1 from O1 into V, and it's going to be just the difference quotient. Like that. Okay. Okay. Is that all right? Okay. So now the statement of this characterization of C1 mappings is the following. Okay. So then the following are equivalent. First statement is that phi is C1. Oh, sorry, I don't want to say that up here. I apologize. I throw the whole I throw the result away if I write it like that. Sorry. I just mean phi is a mapping from O. Sorry, let me get rid of that. Okay, from O into V. Right. Okay, so one of the statements is that it's C1. And then the other statement is that this mapping that I just defined, phi1, admits a continuous extension to, okay, so here I've, in this domain here, I've excluded 0. I've excluded 0, okay, and here I've included 0, okay, and so this mapping is going to extend from this point, from this set to this set, okay. Okay, so it admits a continuous extension, which I'm going to call phi this bracket 1 from O1 into V. Okay, does that make sense? Or do the symbols make sense at least?
Yes.
Okay. So one direction of this seems clear, okay? And that is if you have a mapping if phi is C1, okay, how do you define this thing at points where t is equal to 0? Well, you're going to define it to be the limit as t goes to 0, so it's just going to be the derivative, okay? So it's kind of clear where this where this idea comes from, okay? But let's prove it. Okay, so proof. Right. Okay, so so I'm going to assume now that phi is C1, and I'm going to prove that there's a continuous mapping like this. Okay, so I'm going to define, of course, this mapping, and it's defined, as I just said, in the obvious way. Define phi 1 of t x u to b. Okay, so it's phi 1 of t x u when t is not 0, and when t is equal to 0, it's the limit as t goes to 0. Okay, so what else could it possibly be? Right. So now you need to prove that this mapping that I've defined here is continuous. Okay, so what I know, remember, from phi being of class C1 is that this mapping is a continuous function of its arguments. Okay, so that's not the same thing as this being a continuous function of its arguments, right? So there's a little bit of work you have to do there. So let's do that. Okay. Okay, so to show that phi1 is continuous, we need only show continuity at points of the form 0, x, and u. Okay, because when t is non-zero, okay, then phi square brackets 1 is given by this expression, which is clearly a continuous function of t, x, and u. All right, so it's just continuity when t is equal to 0. All right. So let's let delta let r be a small positive number. Let n be a neighborhood of x, and let's say p. Okay, so n here is in O. Okay, p is in V. Be a neighborhood of U. Okay, such that the disk of radius r centered at 0 cross n cross p is contained in O1. Okay. I mean, this is just the definition of O1 has this condition. All right, so this just says if I choose an x, a t, and a u that are in O, then I can find neighborhoods of x, neighborhoods of t, and neighborhoods of u. So the whole thing is also in O, and so that's all I'm doing here. Right? So I'm just using openness of O. Okay. Okay, and so to be clear, this is the disk. Matter. Okay. All right. So that's first step. Okay. So now we're going to try to write an expression for this thing. Okay. In terms of the derivative, and we're going to do that using the weak integral. Right. So let me just write down some things and then we can see why they're true. Right. So these are just things which follow from just the mean value theorem. Okay. So let me just write some stuff down. Okay. So it's phi. So d phi of x plus s t u. Okay. Then it's u ds. Okay. All right. All right, so let's do a simple calculation on that. And what I'm going to do is I'm going to use homogeneity in the second argument to put a t in there and then a 1 over t out front. Okay, so 1 over t, weak integral from 0 to 1 d phi of x plus stu tu ds. Okay, so all I've done there is I've just used homogeneity of d phi in the second argument to multiply by t there and divide by t there. Okay, so I guess I'm assuming that t is non-zero. Okay. And this, by the mean value theorem, okay, is simply phi of x plus tu minus phi of x over t. Okay, so if you just look at the mean value theorem, you will see that that whole thing is exactly the numerator here. Okay. And of course, this is just v1 of txu. Okay, and the point is that it expresses this thing which we're interested in understanding in terms of a weak integral. Okay, and so okay, and so this is okay for t not equal to 0. Okay, all right. Now for t equals 0, I'm going to write down the same thing. Okay, I'm going to write down this expression. Okay, but now it's going to be trivial. Okay, so weak integral 0 to 1 d phi of x. Okay, so t is equal to 0, so it's just this, like that. Okay, so the integrand is independent of s, and I'm integrating from 0 to 1, so this is just d phi of x u. Okay, now what I'm going to take note of now is simply continuous. So I have this expression here, and I've evaluated that both for t equals 0 and for t non-zero. Okay, so for t equals 0, I got this, and for t non-zero, I got that. Okay, but I know from what we talked about with weak integrals, that the weak integral is going to be a continuous function of the parameter t. Okay, and so, okay, so because the weak integral depends continuously on t, all right, we have limit as t goes to 0, phi 1 of t x u is equal to d phi of t x and u. Okay. All right. Okay. But what do I need? So certainly that's true. Okay, good. But what I also need is I need continuous dependence not just on t, but I also need continuous dependence on x and u. Okay, so okay. Um, all right. Again, by continuous dependence of the weak integral. And so, in fact, I have that phi 1 of t x and u is, okay, so the limit as t goes to 0 is equal to that. Okay. And it's also a continuous function of all of its arguments, t and x and u. So it's continuous on d, n, and p. Okay. So that proves one direction. Okay. So that proves that if it's C1, okay, then this mapping extends continuously. Essentially what it says is that this mapping of its three arguments, t and x and u, extends continuously to the case when t is equal to 0. Good. So this isn't very surprising, but there's to actually prove the statements requires a bit of work, as we're seeing. But there's a payoff for this, and that is some things become much simpler. Okay. All right, so now we're going to assume that this thing admits a continuous extension to phi 1. Okay, so again, phi 1 includes t equals 0. Right. And then we're going to prove that phi must be C1. Right, so this is relatively easy. Okay, so by continuity of this extension, phi 1, we have that the limit as t goes to 0 of phi of t plus x u, oh sorry, x plus du, x plus du minus phi of x over t is the limit as t goes to 0, phi 1 of t x u is equal to phi 1 of 0 x and u. Okay. And so this means, okay, so thus d phi of x and u must be equal to v1 of 0 x and u. Okay, because this is exactly that limit. Okay, and d phi is continuous because phi1 is continuous. Okay. All right. So does that make sense? It's kind of a peculiar looking result, but and we're going to use it in peculiar ways. Um, but as we'll see, it's sort of it's a neat trick. And sometimes it becomes a little bit more than a neat trick. It becomes something which is quite useful. But we're going to use it as a neat trick. Questions about that?
It's kind of it's somewhat similar to writing a function as its Taylor expansion in the first term plus some error.
Yeah, that's right. So t is kind of measuring the, except of course, the sort of error term or the deviation term in the Taylor expansion is just in one direction. Yeah.
Yeah, exactly.
Okay. All right, good. So, like I said, our main interest is in this little result is that it's going to allow us to give easy proofs of a couple of very useful facts. So first fact is going to be that d phi is additive. So we've already shown that the derivative is homogeneous in the second component. So to show that it's linear, we need to show that it's additive. Okay, so what I mean here, of course, is that d phi of x u1 plus u2 is equal to d phi of x u1 plus d phi of x u2. Okay. All right, so this is just like I said, a bit of cleverness. Okay. All right. So let's write down. So we're going to use this trick that we just had, and we're going to work with this thing. Okay, because phi is assumed to be C1. Okay, so here, just to be clear, phi is C1. Okay, so phi is assumed to be C1, and so I know that this extension function that I just talked about is continuous. Right, and so I'm going to write it down for basically, both sides of this equation. All right, so it's going to be phi t x u1 plus u2 is, okay, so it's phi of x plus t u1 plus u2 minus phi of x over t. All right. Okay, so now you do some elementary stuff. Okay, so phi of x plus t u1 minus phi of x. So I do the adding and subtracting stuff trick. All right, plus phi of x plus t u1 plus u2 minus phi of x plus sorry. Yeah, sorry. X plus t. Whoops. Here, let me do this. So minus phi of x plus t u1 over t. All right, so I've just added and subtracted this guy. All right, and now I notice that this is phi1 of t x u1, and this is phi1 of t x plus t u1 u2. Okay. So if you sort through the definitions, that's what you'll get. Okay, so now take the limit as t goes to 0. And right, so here you're going to get exactly this is going to give you exactly that when you take the limit as t goes to 0. This is going to give you that as t goes to 0. And this is going to give you that as t goes to 0. Okay, so it's a neat trick for proving additivity. Okay, another neat thing you can do with this phi1 business is give a relatively simple proof of the chain rule. Okay, let me try to be stylistically consistent. Okay, and so again, this is really easy in this using our little phi1 trick. So let me tell you what it says. Okay, so now I have 3 locally convex spaces, 3 LCSs, U, V, and W. Okay, I have open sets. Let's say N in U and O in V. Okay, and I have C1 mappings from O into V and psi from, sorry, this one will be from N into V. And this one will be from O into W. And I'm going to assume that phi of N is contained in O. Okay, so that's the setup. And this condition simply means that these things can be composed. All right. Okay, and so then D of psi composed with phi applied to x u. Okay, so sorry, let me be a little bit more careful about that. So then psi composed with phi is first of all differentiable, continuously differentiable from O into W, and there's a formula for its derivative. Okay. Okay, and that form, so the normal formula when you're talking about Jacobians, remember, is just the Jacobians are multiplied basically. Okay, well here it's a little more complicated because we don't really have a Jacobian. Okay, but still the formula makes sense, and really it's just matrix multiplication like you have in the Jacobian case, except you're sticking in all the arguments. Okay, So it's d psi of phi of x, okay, applied to the vector, the direction, d phi of x and u. Okay, so that's what the chain rule looks like in this case. Okay, so again, the proof is by mere cleverness, right? We're going to write down the difference quotients and manipulate them using this, phi1 construction. Okay, so I have psi composed with phi of x plus tu minus psi composed with phi of x over t. Okay, so that's the difference quotient for the composition. That's the thing I want to calculate. Okay, so I'm going to rewrite that as follows. Okay, and it's just, again, a simple adding and subtracting of things in the right place. Okay, so it's psi of, okay, all right, so instead of okay, so this is psi of phi of x at tu. Okay, so I'm gonna add and subtract something to that, right? And the thing I'm gonna add is phi of x. Okay, and so I need to subtract it, and so I'm gonna organize that subtraction in the right way. Plus t phi of x plus tu minus phi of x over t. Okay. Okay, so that's this is just that. Okay, so I've just added and subtracted phi of x. All right, then I still have the other term, which is minus psi composed with phi of x, and that whole thing is divided by t. All right, and what's the benefit of writing it in this of organizing it in this way? It's that you recognize that this, if you think about these one mappings, so this is psi 1 of t phi of x phi 1 of t x u. Okay, so you have to stare at this for a second to see that that's true, but quickly you can recognize that it is. Okay. All right, so so this thing is continuous in xt and u. Okay, so let me write that down. Okay, again, because it's a composition of continuous things. All right. And you notice that if I evaluate this thing at t equals 0, okay. Okay, so I go psi 1 of 0 phi of x phi 1 of 0 x and u. Okay, well, what's that? Well, first, this thing is by the definition of phi 1, this is d phi at x u. Okay, and then again, this at t equals 0 by definition of psi 1 is going to be d psi 1 evaluated at this point and then this thing. Right? So the point is that's exactly the thing we're trying to calculate, or the thing we're trying to show. Okay, so this is d psi at phi of x d phi of x u. Okay. Right, and that does it, right? Because what do I need to show? I need to show that the limit as t goes to 0 of this thing is equal to this thing. Okay, and first of all, the limit exists because this is a continuous function of tx and u. All right, and then moreover, the limit is equal to that. Okay, so thus, so let me summarize all that. The limit as t goes to 0 of psi composed with phi of x plus tu minus psi composed with phi of x over t is the thing I want it to be. Okay. And moreover, it's a continuous function of x and u. Because because this thing is a continuous function of x and u. Okay. Okay, and that's the chain rule. All right. So that's I think a pretty slick proof of something which is often quite messy if you look at proofs of the chain rule. And so this is kind of a neat proof of the chain rule, and it's possibly even an improvement on the proof of the chain rule in the normal case. But there's a little bit of baggage with all this, psi 1 and phi 1 business.
I mean, I think this is quite optimal. Like there's
Yeah,
it's
yeah,
a
I
bunch
think
of
it's a
calculations.
very, very neat proof. It's a very neat proof. Yeah, I agree. It's not
Yeah.
my idea. So this comes from a early 2010s paper by Helge Glockner.
Aha, okay.
Yeah.
That's nice.
Okay. Right, so I think this is an excellent place to stop, and so next time, what I'll do is talk a little bit about some of the aberrations in this theory of calculus compared to the theory of calculus that you know about, and basically what's the difference between this little d that I'm using here and the big D that the Jacobian that you talk about in multivariable calculus. Okay. All right, so that's the end of our lecture for today. And again, you're welcome to leave. And if you want, you can stick around and ask me some questions.